yeah kan lote kan missionary te min zirtir na train chuan amoi lo le azurui wain ruin om su ti ka bible thu min chania ring tu de chu ma rui bol te va in va li thalawa zu in ti wall out ka om poi thak ri chu lawa u ran dong bol tu kan ni chuan sengin tiangin kangai thu tak te bur lo ki chuan tiangin regular taka in tur chu ka pe lo hrim ka pe lo hrim so grab tui vel te tui ve me ka te grab tui thum tuk ni lo in a fermented tle man om ti te wait. Okay, guys, welcome back. Oh. So we'll continue our lecture and hopefully we can finish our syllabus today. And we may utilize the remaining lectures for revision and all. So yeah, the attendance link, the Google form link is provided in the chat box. So if those of you who join a little bit later, please request your classmate to copy and paste the Google form in the chat box again. Only those attendance entered in the Google form will be counted for your attendance. Do not type your roll number in the chat box. Whatever is extracted out of the Google form, it will be counted for your attendance. So yeah, someone please copy and paste the attendance link, Google form link in the chat box. All right. So this is what we have discussed yesterday, and we'll continue with another problem. So the problem that we are going to discuss, the first problem we are going to discuss today is the one shown here, which is so that every second rank tensor can be expressed as sum of symmetric and skew-symmetric tensors. So from the previous class, we have defined what are symmetric and what are skew-symmetric tensors. Symmetric means you interchange the indices and the identity or the property of the quantity or whatever is represented by that tensor will remain unaltered. Antisymmetric means if you interchange the indices, the quantity represented by the tensor will change its sign. So aij will become minus of aji, like that, right? So here we are going to consider a second rank tensor, and in fact we can consider any second rank tensor, whether it's a contravariant tensor or covariant tensor, it doesn't matter. So let us say we take this contravariant tensor. Here, as you see, the indices I and j are in the superscript. So these are the contravariant indices. So contravariant indices. Just a minute, I have a missed call. Oh, hello, Sarmapu again. Oh. Oh. Oh, mỗi quý lắm bằng hồn rồi thì nó mỗi quý power station hay Pubi mà thế hồ tí tí là ngay cần electric in charge thế ô Pubi mà hiểu phone tốt mà number nè mà class cái này ngồi Pubi mà hiểu cần để xin chúng mà ngồi phone này sẽ cái class lạc lọ đi na SU in tung en biếc SU in tung en biếc Oh, I need to call luxury him or who be here. Mol pui lam pang mo ka to lo ke chuan ka to lo tri ke hian mol pui lam pang power station phone number reng mo ke chu ka hring lo wa bia ma chu ka be thai tho chuan sa om zio mu tuk chu lo nga ole le just a minute now guys. Oh pubiem imo anon phone to thu ching khre siu lam pang khan khulai tu nei current kan nei lo ta tro hemi hi mol pui lam pang mi kha power distribution khoi tu te kha an mani ho kha contact nai nei chuang lo em khai nei em eng tinge nei chung bi lo mo eng tinge current hi om le theng le di vel te kha a hriat dan om ngem le an ti deuh mai mai a san chu badminton practice chu ran nia khu an practice ve lo kra dam lo chuan mo nei ngei nei hrebik lo deuh hlek ami khatiang current chung chung cha o mol lu zo saksin thengem leng tikang en ang mai hriat chuan o current om thailo view don chuanin an practice thei mi lowa badminton player ro khon an boi ve deuh hleka chu o lo zo ko saksin mai khong ein e boi tho la ma okay. So yeah, what I was saying, yeah, I think we are talking about this contravariant tensor. So here the statement says that a contravariant, any tensor, any second rank tensor can be expressed as just 1 minute. So Aij, yeah, we can consider any second rank tensor. So any second rank tensor, if you take it, you can express it like this: Aij. See, if you write, this Aij, you can write it as half of Aij plus half of Aij. So half of Aij plus half of Aij is Aij. So then in this expression, you can add and subtract half of Aji, you add, you subtract also half of Aji. So the same quantity you add and subtract to this expression, and then combine these two terms and combine these two terms. So this second rank tensor, this second rank tensor, you can combine it like this, you can combine it like this, right? So now you can put the first term here, half of Aij plus Aji, as see this is an addition of Aij tensor and Aji tensor. If you just put this addition of two tensors, two contravariant tensors as another contravariant tensor, which we call it Cij, right? So if you are adding two contravariant tensors of rank 2, it will result in another contravariant tensor of rank 2. That's it. So you can write it as Cij. And similarly, you can also denote the second term, that is subtraction of two contravariant tensors, as another new tensor called dij here. Now, if you look at this first term here, which is Cij is equal to half of, oh, just a minute. Oh, hello, PPM. Hello. Oh, yeah. Khoi amo nan tho ai te la mo online nan sing same ga mo ani chu voin chu exercise ve lo la set me lo kan zir lai po chu practice thei lo ni chu te ki nam lo chu kan thri lang o kha chun chang khru wa alo o me oh, I'm so disturbed, sorry. I have to make another call. Oh, hello. Hello. Imo sarma pui khalo khilamo kan electrician te kal tangin khumi hemi kan ke mani power supply line monitor tu te kan ke mo ani chuan soidan chuan ITI kon line engamo transformer engamo ni thalo ma chu na an thoka an khoilak lo wangin line an kat ria an zo hun tur an thei ri lo ni chu wang chuan kan zirlai kan badminton player ho te kha tu na ri join chuan lo workout se exercise lo la se ni mai oh nakin to wa chuan ron siam thave me ang load setting ni lo in chu line an khoilak lo wa ni mo an zo hun tur chun la chuang lo wa se an ti zo ve me ang nakin to wa chuan oh le lo hrit me ro ni la So if you consider the first part, which is addition of two contravariant tensors of same order, same rank, you will get this new contravariant tensor of same rank. Now, Cij is this. Now, let's say you interchange the indices. Yeah, please mute. Let's say you interchange the indices, that is Cij, you write it as Cji, interchanging the indices here, Cji. So Aij becomes Aji, Aj becomes Aij. Now you get this term after interchanging indices. Now, if you rearrange it, you can rearrange it as this, and which is same as your Cij by definition here. So that means the first term here is having the property that Cij is equal to Cji. That is, the first term is your symmetric tensor. Okay, the first term is symmetric tensor. Now, if you look at the second term is subtraction here, which we defined as Dij. Now, if you interchange the indices Dji, this becomes Ji, this becomes Ij. So if you look at this term, if you take a common factor as minus here, you will get this term. So this term is your Dij. So you see that the second term is having the property that interchanging of the indices will result in minus of the original value. Dij is equal to minus of Dji. Therefore, you can conclude here that this contravariant tensor of rank 2 can be expressed as sum of symmetric Cij and antisymmetric Dij tensors. Sum of symmetric and antisymmetric tensors. Okay. As simple as that. This is again very simple problem. Prove that A subscript alpha beta subscript alpha beta means, sorry, superscript alpha beta. Superscript means alpha and beta are the contravariant indices. So this is a contravariant tensor of rank 2, and this is also contravariant tensor of rank 2. When added to or subtracted from each other, they still behave as a tensors of the same type. Now, in order to know that whether they still have they still maintain the contravariant tensor of rank 2 property, we have to see the transformation relations. So in order to see the transformation relations, we define the corresponding values in prime coordinates as A prime mu gamma, the two contravariant indices B prime mu gamma. So you can write the transformation relation between a prime mu gamma and a prime alpha beta. Mu corresponding to this mu contravariant index, you have alpha contravariant index, and if they are contravariant indices, the transformation coefficient will be partial derivatives in which the prime coordinate variable is in numerator. That is, x mu prime is in numerator, x alpha is in denominator. And here you have the second index here in the prime coordinates gamma, and the second index, the corresponding index is beta, and corresponding to true contravariant indices, the transformation coefficient is this. Similarly, you can write the transformation relation for B alpha beta tensors in measured in unprime coordinates, and the corresponding values measured in another prime coordinates. Now you can perform addition or subtraction, whatever. If you add or subtract like this, adding and subtracting, this is what you get, right? So if you add and subtract here, you will find that this term and this term can be taken as a common factor. Okay, so addition or subtraction of this thing will have this form, and addition or subtraction of this two contravariant tensors also will have this form. And here you find that the transformation coefficient is such that the prime coordinate variable is in numerator and prime is in denominator, and prime is in numerator and prime is in denominator. So after addition and subtraction, here you see that it still maintains the transformation coefficient for contravariant tensor of rank 2. It still maintains transformation coefficient for contravariant tensor of rank 2. So if that is the case, then we conclude that whatever quantity we obtain out of addition or subtraction of these two tensors results in tensor of the same type, that is contravariant rank 2. Tensor of the same type, contravariant rank 2, because it involves two partial derivatives, so it's rank 2. And in the partial derivatives, the prime coordinate variables are in numerator. So the resultant of this subtraction and addition of two tensors, two contravariant tensors of rank 2 results in same type of tensor. All right. Now, this is another very simple problem. If A mu sigma and B mu sigma, see, if you look at this, mu is in superscript, sigma is in subscript, then mu is the contravariant index, sigma is the covariant index. So if a particular tensor has both contravariant index and covariant index, this is a mixed tensor, right? So if these are mixed tensors of rank 2, then prove that their sum and difference are also types of the same, are also tensors of the same type. So in order to see that whether the tensor property is mixed tensor property is still maintained or not, we have to look at the transformation coefficient. If the resultant of subtraction and addition of tensors is another tensor of the same type, that is mixed tensor, that is if it involves the same transformation coefficient. If it involves the same transformation coefficient, then this this proves the theorem here. This proves what is proposed here in the problem, right? So in order to do that, we have to write the transformation coefficient. In order to do that, we have to write the transformation relation. If we are going to write transformation relation, then we first define the corresponding values in prime coordinates as this A prime alpha beta, B prime alpha beta. And now we are going to write transformation relation between these two. Here we see that alpha is contravariant, mu is contravariant index. So correspondingly, the transformation coefficient will be like this. Beta and sigma are the covariant index. The corresponding transformation coefficient will be like this, so that the prime coordinate variable is in denominator here. Yeah, and similarly, we can also write for this. Now you can perform either summation, addition or subtraction. So if you perform it like this, here in these two terms on the right hand side, this these are common quantities, these are common factors, so you can take it as a common here. And if you look at this addition or subtraction in unprimed system, addition or subtraction in the prime system, they are related with this transformation coefficient. They are related with this transformation coefficient. So from this transformation coefficient, we can see that prime x prime alpha is in numerator, x mu is in denominator. That means alpha and mu are contravariant indices, and here x prime beta is in the denominator, means beta and sigma are the covariant indices. Beta and sigma are the covariant indices. So this proves that the same transformation rule, that is the two partial derivatives here for the mixed tensor, is still maintained. So therefore we can conclude that the resultant of subtraction or addition of these two tensors, mixed tensors of rank 2, is still mixed tensor of rank 2. Okay. Now, yeah, this is second last I would like to show here. If a lambda and b mu, if you look at this, lambda is in superscript, so this is a contravariant index. B mu means this is a covariant index, are the components of contravariant and covariant tensor of rank 1. It has only one index, so rank 1. So that the product are the components of mixed tensor of rank 2. So in order to prove that this product is a component of mixed tensor of rank 2, we have to show that this product obeys the transformation rule for mixed tensor of rank 2. We have to show that this product obeys the transformation rule for mixed tensor of rank 2. So A prime, in order to do that, we assume the corresponding values in prime coordinates as A prime alpha, B prime beta. Then we write the transformation relation between this and this. A prime alpha, A alpha, A prime alpha, A gamma. This you write. And see, this being the contravariant index, the corresponding partial derivatives of the coefficient will be such that x prime alpha is in numerator, x gamma is in denominator, x lambda is in denominator. And here transformation relation between b prime beta and b mu, if you write, you know that these are two covariant indices. So the partial derivatives will be such that the prime coordinate variable is in denominator. Now you multiply them. You multiply the left side, you multiply the right side. When you multiply the right side, this is what you get as a transformation coefficient. If you look at this transformation coefficient, the first term here, alpha gamma, tells that alpha is x prime alpha is in numerator, x gamma, x lambda is in denominator. That means alpha and lambda are contravariant indices. And similarly, x prime beta is in denominator, means beta and mu are covariant indices. So we can denote the product like this: c prime alpha beta and c prime alpha beta and c lambda mu. C lambda mu, these two terms, they follow the transformation relation for mixed tensor of rank 2, because the transformation coefficient involves these two partial derivatives. These two partial derivatives are such that the prime variables are in numerator here, denominator here. So one is the covariant, one is the contravariant index, right? Now the last one, so that A lambda, so lambda means lambda is in superscript, means this is a covariant tensor of rank 1. There is only one index. So that A lambda x mu is not a tensor, right? So in order to prove this, we are going to start by writing the transformation relation again. So in order to do that, we assume the corresponding quantity in prime coordinate as A prime alpha. A prime alpha and A lambda, they are related like this. Del x lambda, see, they are covariant indices, means del x prime alpha, this is in new denominator. Covariant indices means in the partial derivative, it will be in the denominator, the prime coordinate variable. The n prime is in numerator here. Now you differentiate it with x mu, differentiate with x mu. After differentiating with x mu, you differentiate this lambda term, a lambda term, and then you can differentiate these two terms, the second term. So differentiation by product rule you apply. So it results in on the right hand side, it results in two terms. So even though this is a differentiation, in an prime system, we have this additional term. Because of this additional term, this quantity cannot follow any tensor transformation rule. So if it cannot follow tensor transformation rule, then this quantity, that is the derivative of a lambda, is no longer a tensor. Okay. So I think with that, I will conclude our lecture today. Please type your attendance in the chat box. I will not take class again this week, and hopefully next week I will see where we need revision and all. Okay, with that we complete the syllabus. You can come up with your queries, uh, whichever topic you would like me to explain once again. Otherwise, I will start giving assignment. Those assignments you have to do it. So from next week onwards, assignments will be provided to you. You have to complete the assignment and submit to me, and then we can award your internal marks based on that. All right. Take care, everyone. Do not type your attendance there in the chat box. Only in the Google form. Those who type your attendance in the chat box, your attendance may not be recorded. Only in the Google form. Okay.